All right, we're going to continue talking about forces. In this case, we're going to look at we're always going to have Newton's 3 laws in the back of our mind, right? The fact that things are going to stay still unless a net force acts on them. The equation F equals ma, and the concept of action, reaction, and they're all related, right? They're not 3, say, completely separate laws. They're 3 parts of, I guess, the way that motion happens, all right? So the first thing we're going to look at is just this concept or idea of if I have an object at rest on a surface in a gravitational field, okay, we have to take a look at what's going on here, right? So we've got the force of gravity acting down, and we will call this weight, okay? This will be known as weight. And so what we'll do is we'll write it like this. W, weight, which is the force of gravity, is equal to whatever mass we have here times the acceleration due to gravity, which we call g. So weight equals mg, okay? If there were no tabletop, this object would accelerate. It would have a net force on it, and there would be no, counteracting force. But since it's at rest, it's not accelerating, we know that there's another force at work that is equal and opposite to that force, okay? We can call this a reactive force. This force changes in lockstep with the weight. So in other words, if we were to say increase the weight by adding more mass to this object, say it's an empty bucket and we start pouring sand into it, okay, then the upward force will grow as the downward force grows. So this is the normal force, and it's a reactive force. Okay, and it is exactly equal and opposite to the force of gravity at all times. Okay, so normal, this is a reactive force. Changes when this changes. Okay, so that's a basic kind of principle in physics. All right. The next thing that we might be interested in doing is maybe we want to push this object along, right? We want to push it along. So if we were to grab it and we were to slide it along here, right? We want to push it along. In order to do that, we need to apply a force on the object. We're going to use our free body diagram kind of way of doing this. So we're pushing it, right? So here you are, you're small but mighty, and you're just giving this a good shove, okay? And you're making it accelerate, okay? Or even just say, making it move in general. Well, you will note that if this moves at a constant velocity, so in other words, there's no acceleration, say we're just moving it along at a constant velocity, well, there must be then a force counteracting this, right? So we can call this your FA, the force that you're, say, attempting to accelerate with or push it along with. And since it's not accelerating, it's just traveling constantly, right? Your FA must be counteracted by another force. We call that the frictional force, okay? So friction is the interaction between these two surfaces. Okay? And to a point, the frictional force is also reactionary, and I'll tell you what I mean by that in just a minute, okay? We would also have, of course, our normal force and still your force of gravity, okay? If I make this object heavier, right, I have to push it harder because the normal force has grown, because gravity has grown, and it turns out that the frictional force and the normal force are related to each other, okay? So the frictional force is actually proportional to whatever the normal force is, all right? So if the normal force goes up, i.e., you add mass to this, then the frictional force will also go up. Why does this happen? This happens because The surfaces of these objects at a microscopic level are rough to an extent, right? We looked at it with a really fine microscope, we would find a roughness here, okay? There's also some electrostatic effects. I don't really need to totally consider those at this point. Just be aware that they're there, okay? So, in other words, if these are being, if you want, pressed together, okay, as, you know, a normal and a gravitational force, and you're trying to move it like this, as this moves along, it essentially has to, if you want, bump along, right? And there's like a resistance to that. I'm sure if you've ever tried to push one rough surface over another, you realize that there's, you know, more effort required when you squeeze them together more. Does that make sense? Okay, so as normal force grows, so does the force of friction. And you can actually measure this, and you can write it in this way. Force of friction is equal to mu times Fn. What's mu? It's just a frictional constant, or coefficient if you want, that is unique to the two materials and the scenario that's going on there, right? So this box might be made of cardboard, this surface might be made of asphalt. You're going to have some coefficient of friction. As you raise and lower, friction raises and lowers in lockstep. This value makes one thing equivalent to another. So this is a unitless value that simply relates one value to another. You know, if you change this to being ice and this to being steel, the coefficient is going to change, but this concept stays the same regardless. Okay, so something to think about here in terms of normal force and force of gravity. Something to work your mind around a little bit is, you know, imagining that you are now in something like an elevator, okay? And let's say that elevator is accelerating upward, okay? You know, you're at the local shopping mall or whatever. It's accelerating up at, say, 2 meters per second squared. What does that mean for you inside? So I like to think about this as if you were standing on a scale outside the elevator, okay? Here you are, okay? When the elevator is still, it just reads your weight. Let's say it reads, I don't know, 980 newtons, okay? What does it read when you start accelerating at 2 meters per second squared up? Well, how much do you weigh in kilograms? What's your mass in kilograms if when this is still, it reads 980? Probably 100 kgs, right? So what that means then is the force of gravity on you is 980 newtons, okay? So 980 newtons in a still elevator. And that means that the normal force when the elevator is still is also 980. Okay, that's what the scale is going to read. But what happens if we accelerate up? Well, that means then that the normal force has to supply not only 980 newtons, but it also has to supply more force to accelerate you upward, and that's going to be equal to m times whatever acceleration you have, right? That's how much heavier you're going to be. So 100 times 2 meters per second squared, 100 kgs times 2 meters per second, another, we've got to add another 200 newtons to this. So all of a sudden this is going to read 1180 newtons while you're accelerating upward. You have gotten heavier. Your mass has not changed, but your weight has increased, right? You need, the floor has to accelerate you up at 2 meters per second. If that is supplied by the springs in the scale, which are calibrated, they're going to weigh heavier. It's as if you have added on an extra, 200 newtons worth of mass to yourself, 200 newtons worth of weight to yourself, okay? And the same is true now, like let's say the elevator starts to slow down. In other words, the acceleration flips to 2.0 meters per second down. Well, now what's going to happen is the normal force is going to reduce, right, by that amount. In other words, gravity, there's going to be an out of balanced force. There's going to be a net downward force when you add gravity to your upward force. that's going to be 200 newtons downward. So in other words, this is going to weigh 200 newtons less. So 780 newtons. So you go through this fluctuation when you ride in an elevator. As it accelerates, okay, you weigh more because the normal force has gotten larger to help put you up. When you slow down in an elevator, or vice, if it's accelerating downward or whatever, when the acceleration is pointing downward, your weight reduces during that acceleration, and it will be shown on a scale. If you think about it in terms of a scale, it's a fairly, I think, easy concept to understand, right? The other interesting thing is that while you're going up but slowing down, or you're stopped and you're accelerating downward, the normal force is lower, and therefore the frictional force will also be lower. So while the elevator is accelerating or has a downward acceleration like this, it'd be easier to slide things around on the elevator floor. And as it's accelerating up, it would be harder. Okay, so all of these different forces are related. Okay, are you with me? So let's move on to another scenario here. What if I take something and I put it on a sloped surface? Now, we have some more stuff to think about here. Okay, so let's do this. You have probably experienced the scenario where you take an object and you sit it on a surface and then you lift the surface up. Like you might do this, you might even try this, just get a ramp or something, put a little ball on it, you start to pick it up, you don't have to move it too far before the object will start to slide down. So how do we explain this? Well, when the object was just sitting flat on the surface, the normal force and the force of gravity are parallel to each other if you want. Opposite in direction, but parallel in terms of their plane. If, however, we lift the surface, we have to consider that the normal force is not the same as it was before. Okay, the normal force always acts perpendicular to the surface. I feel like I can't get this quite straight and it's bothering me. Nope, good enough. Okay. So let's just put in our other line here because we're going to measure from it. And we need to know that the angle here is going to play a role. So we're going to call that angle theta. Okay. So how has this changed the scenario? Well, what it's done, okay, gravity will always point down towards the center of the Earth like that. However, the normal force points up like this. Okay. So there's the normal force. So these guys are both, these guys are both acting on this object now, right? But from before we learned, and remember this is perpendicular to the surface, before we learned that when more than one force is acting on an object, we sum those forces together. So if we were to move these such that they are tip to tail so we can do vector addition, the sum of these two vectors is going to give us a net force that looks like that. Okay, so the net force on this object, F net, right? The sum of this guy was Fg, and this guy was Fn. So the sum of Fg plus Fn equals our net force. Now the question is, how do we sort out what these values are? One thing that may or may not be important, I'll show you why it's actually not important, is the mass of this object. Okay? The mass of this object is important to know what the actual normal force is or what the actual force of gravity is, but it turns out it plays no role in what the acceleration of the object will be. Okay? But that's for a little bit later. One other thing that we need to also consider is there's still friction in this scenario, right? And friction will act opposite to motion, right? It's also a reactive force if you want, okay? And that's based on the new Fn that is actually going to be changed from what it was when we were just sitting flat on the surface, okay? Before this object starts moving, Ff will always equal our F net. and we're just going to change the name of this from F net. We're going to call it FA. It's the force attempting to accelerate this object down the plane, okay? So FA and FF, they remain equal to each other, okay, until the object starts to slide. And if it slides constantly, then they are exactly equal to one another. If there is a net acceleration down, then FA has become larger than FF. We'll get into that in a little bit, or possibly in another class. So let's just quickly make this connection. And often this is not quite how this is drawn. Physicists like to actually draw this in a slightly different manner, so I'm just going to do that. Okay, so what we're going to do is we're just going to move some things around. So this is generally drawn actually like this. It's the same thing. Physicists just like to do the tip to tail like this. Okay, so like this. So just to relabel things correctly. There's our normal force. There's our gravitational force. And there's our accelerating force. And it turns out that theta here is the same as theta here. We can basically prove that if we need to. Okay, we can say this is 90 degrees. And we can say that this is 90 degrees. Okay. We can say that this is alpha. And then by equivalence, this is alpha. Okay. So if that's alpha, then that has to be theta up in this corner, right? And since these triangles are cut perpendicularly, okay, and this here, right, value should be the same as this here value, right? Because these two lines are perpendicular. So we can prove by geometry that these two theta values are the same. Does that make sense? Now we're just going to redefine a couple of things here. We're going to say that the normal force in this case is going to be based on Fg, okay? So if we know the mass of this thing, we can say that Fn is going to be equal to Fg times the cosine of theta. And we're going to say that Fa, right, this down here, should be equal to Fg times the sine of theta. Or, since we know that Fg is equal to mass times g, we can break it down into this. Mg cos theta and mg sine theta. So for example, let's do a frictionless system, e.g. a frictionless ramp has an angle of 10 degrees. A 10 kg mass is placed on it. Find acceleration. Okay, so basically all we got to say is Fa in this scenario is mg sine theta. Okay, and we know mass times acceleration is mg sine theta, so we could say this: ma equals mg sine theta. And actually we'll learn the mass itself does not matter in this case. So A just equals G, 9.81, times the sine of 10 degrees. We get 1.7 meters per second squared, okay, on a frictionless round.